Okay, so we are continuing with our infinitesimal screws, and so we start by saying that so this is this screws, wrenches, motors, okay, which is not in hardware store, it's all mathematical. And we say that we are just taking a line and we are just saying that there is something called a pitch parameter h, which will associate with that. And so there are four infinities of lines in the space. So we have 5 infinities of screws in space. So there are two systems, okay. There is Poinsot's system and there is Moses's system, okay. So the ray is Poinsot's and this axis is Moses's, okay. So there are almost two, so we will go through with two parallel definitions and then intersperse it with commonality between the things. So we start off by looking at this. So if you take any system of forces and couples acting on a body, that can be reduced to resultant, that you have known for a very long time, right, expressed, except that here I am doing it as a pair of parallel vectors. A force F along on the line of action together with a couple free vector C parallel to F. Okay. Now this combination of F and C is called a wrench about a screw, and typically they use a dollar to represent it. Okay, so this is called the Poinsot's axis. Okay, and the interesting part is you write the couple as a scalar times the force. Okay, so it is not actually two vectors, it is one vector and something which is scalar times the force. Okay. Now what Mozzi had come from was that he was looking at displacements of the body. So he said any given infinitesimal displacement of body can be expressed as a pair of parallel vectors. Similar definition, angular velocity component omega about an axis and then together with a translation velocity component parallel to that. So again you take the combination of omega and the tau and you call it a twist about a screw and you call it Moses's axis, okay, in which you get tau is equal to h omega. Okay. Now so this is very basic definition. Now the real usefulness from this in this comes from is that when you can start combining these wrenches and twists together. Okay. So you define the intensity of the wrench as F, okay, except when H is infinity, in that case it becomes a pure couple. Okay. So then you use the C as the intensity. Similarly, there is amplitude of a twist, which is essentially the omega, okay, except when H becomes equal to infinity, then you use the translation as the what is called the amplitude of the twist. Now, so the important results are here that any given system of wrenches acting in parallel on a body reduced to a single resultant wrench about a screw. So you can literally add up the wrenches together and similarly if you have, now this is if you take a body, you have a wrench, you have a force and a moment applied, you have force moment combination applied, you have force moment combination applied here, that is acting in parallel. You have a body, there are multiple forces acting on it. Okay. The corresponding axis representation is that if you have a system of twists acting in series. So if you look at the manipulator that you looked at, there was a joint and then there was another joint, so it is a series of motions which are acted one upon by the other, then you can say that you can reduce the end effector motion to a single twist about a screw. Okay. So, rest is just a very simple statement. If you take a range of intensity f and pitch h acting on a body, then the x, y, z components of f are f times L, f times m, f times n. F is a scalar, and this L, m and n are basically the standard screw notation ones. Similarly, for the other side, you just define it as omega L, omega m and omega n. Now comes the part. So, you take the normal vector from the screw to the origin. Okay, so then R essentially will become equal to p square plus q plus r square raised to the power half, the magnitude of R. So, if you wanted to find the resultant moment about the origin, that is f cross r plus hf. Okay. Similarly, the velocity of the point at the origin is omega cross r plus h omega. And if you look at the resultant moment acting at the origin, then it becomes f times p, which was the component, plus this term HL. Okay. Similarly, f times q plus hm, f times r plus hn, and here you get omega p plus hl, q plus hm, r times hn. So, these are identical definitions which are just going, except that these are the velocities of the point which is instantaneously at the origin. So, what you do then next is that you write p plus hl as p star, q plus hm as q star, r plus hn as r star. If you do this, then you can write essentially m as f p star, f q star, f r star. Similarly, here omega p star, omega q star, omega r star. So, this is just nomenclature, that instead of, so you are replacing, earlier we had L M N for a line, L M N P Q R. Now, with the h thrown in, we will end up with L M N P star, Q star and R star. And so, these correspond to real terms. So, you then land up with what is called screw coordinates, which is L M N, P star, Q star and R star. Now, you will notice that now if you dot L, M and N with P, Q and R, you will not get 0, because they are modified by the H terms. It is not fully perpendicular, orthogonal. So, there is component. So, this P star, Q star, R star has this component HL, HM, HN, which are along the same direction. If you now take this set of direction ratios, right, L this is equal to LP star, okay, and then if you know that say LP, now if I want to add up LP star, MQ star and NR star, right, I know that LP plus MQ plus NR is equal to 0. So, I will be left with H L squared plus H M squared plus H N into N squared. So, this has to be equal to LP star plus M star Q plus NR star, and so you get the pitch is equal to this divided by LP, this divided by L squared plus M squared plus N squared, and if this has been normalized to be equal to 1, then the pitch simply becomes equal to, I mean that is algebra, just pointing out, getting things in a. So, the only thing is we look at the screw at infinity. Okay. So, if it is an infinity, then these three become equal to 0. Okay. The pitch is infinity, and this then looks identical to line at infinity. Okay. So, it is a pure translation either way. So, line at infinity, screw at infinity are mathematically the same thing, and they give you pure translation. Now, everything we defined so far was based on a point. Either we are calculating the forces and moments at the origin, or we are looking at velocities at the origin. Now that is not always the point of interest, right. So for example, you want to know the end effector velocity. There is no point finding out everything in the coordinate system, what is happening to a point which is attached to the end effector at the origin of the coordinate system. That is not so useful. So you had a relation earlier of where for p you wrote p minus 1 upon omega yz mn, right, and I asked you to try and prove it last time, and similarly just replace p star by p star minus 1 upon w yz mn, okay, if xyz is a general point, okay. Similarly you will have expression for q star, r star, okay. So this is identical essentially to the case of the line. So far are you reasonably with me? You will not get the full thing until you solve problems, which people don't seem to be doing. So that's the next step, I guess. And anyway, this is so we now introduce this concept called reciprocity. So if you have a body which is free to twist about a screw, right? Can you give me an example of that? The door, right, that is free to twist about a screw which passes along the hinges, okay, it's most common. Then you also have screws, but let's take that. So it says that, and a wrench is applied to the body about another screw. How come I missed this late night? Then the instantaneous rate of working is, now look at the way how this is being combined. So you have L, M, N, P star, Q star, R star, okay, and then we write P prime star, Q prime star, R prime star, and here you write L prime, M prime, N prime. So essentially you have two screws, so you take the first three here and you dot it with the second, and you take this and you dot it with these two, so it's just crossed, okay. So it's not a dot product, it's a little different, and that's why this is called reciprocity. That's why it's called a different condition, it's called the condition of reciprocity. So if essentially you have two screws, then the instantaneous rate of working is this. So you have this line, and then if I suppose I open the door and its door is like this and I am pushing exactly along that, then I can define another screw which is in this line. So it's free to move about that, so you define a twist about that, and I am pushing in this direction, so you define a wrench in this direction, okay. Or maybe this is a better example, right. So you are free to twist about this axis. So you can see there are many conditions of doing work. So if I push in this direction, if my wrench in this direction, it is doing work. However, if my wrench goes in this direction, then it does not do any work.
Your wrench should not intersect that.
Well, if yeah, that's what it says. Intersection is not defined on this. It's very difficult, right? Well, if it intersects, intersection a little difficult. So you use this condition that that a wrench can do no work on a body constrained to twist about a screw when essentially this is satisfied. This is equal to 0, and this is called the condition of reciprocity. Okay, it is difficult because the perpendicular distance between two screws is not defined properly. So you cannot define the distance between a twist and a wrench either. Okay, so you have to evaluate this. You have to evaluate this term, and then find out what the value is. So if the rate of working is 0, then you are not doing any work, so you will not get the other thing to move. That will not gain any kinetic energy. So if it is static, it will remain static. If it was moving with a constant velocity, it will move with a constant velocity, so on and so forth. Okay. So this is a condition of reciprocity. Okay, and from those who are linear algebra buffs, okay, this is not a valid inner product. Let's look at a simple application, and that's all we'll do today, and I'll go very slowly. Okay, so you should understand what the operations are. So first let me explain what the problem is. So I have this funny mechanism where there's a cylindrical joint here and a cylindrical joint here, right? So then if I try to hold it using this end of it and I push on it, right? So I should be able to pull and push it in some direction, and some directions I will not be able to pull and push it. Why is that? Because if I want to pull and push it in any direction without any restraint, then this should have had 6 degrees of freedom, isn't it? But it does not have 6 degrees of freedom. It has only 4. You know, there is this translation along this, there is rotation about this axis, there is a translation about this axis, and there is a rotation about this axis. But if I ask you, where can I apply a force with this? How do you answer that, is the question. Now, these things become important, and what are they important for? It is not that somebody is going to make a funny thing like this and ask you to figure out once you go out there as to what will, where can you apply a force. It comes in much more simpler, supposedly simpler applications. If you have a shaft and it's rotating, you want to measure the rotation of the shaft. How will you do that? You want to attach a potentiometer, encoder, something to it. So the shaft has an axis, the potentiometer has an axis. Now what are your requirements? When the shaft turns theta, you want the potentiometer to turn theta. So you want to join these two together, right? And you guys have all been to a machine shop. So if I tell you, okay, now mount it so that this potentiometer is aligned with the shaft, you know what's going to happen, right? It's going to be anything from half a millimeter to 1/10 of a millimeter off, depending on how good your machining abilities are. So what happens? The shaft and the potentiometer run the eccentric. If it's a BTech project, it works fine. You can come and show it to your supervisor and examiner. But if it's industrial product, it gives up. It will break down, fail, you rub things out. So if you're mounting these kind of things, so what you realize is that, look, I just want these two thetas to be coupled. Everything else I don't want it to be coupled. So I want to mount this potentiometer such that it is free to translate just a little bit in this direction, maybe move back and forth so that the coupling works. And if these two shafts are not aligned correctly, I want this to be able to align like this, but I do not want it to be able to move in this plane. Right? So something as simple as that, when you want to design it, you have to go through this kind of a route. Okay, so don't think that what is being taught here in this course, advanced robotics, is only got to do with things which are moving around in space in a large manner. So you can also deal with small displacements and make these kind of adjustments in mechanisms, right? So if you are making a satellite positioning system, if you are making a scanning electron microscope, a focus ion beam, you know what that is, right? Some of you know what that is. Okay. So yeah, so for these kind of machines, when you are looking for precision of that kind, you need to get into some of this theory to be able to design it correctly. So we will not cover it in this course, but just for a preview that it's not used only for doing this funny problem like this. Though this is what you will get in the exams, funny problems like this. Anyway, so now the deal is, so what wrenches can be opposed by this mechanism if the load is applied to the last arm? So the answer is the wrench that is reciprocal to all the screws representing the joints. The answer is very simple. I have to find the wrench which is reciprocal to all the screws. So now what is the screws here? You take this one, what is on? Pointer options, arrow options, visible. So there is a screw, this is the degree of freedom along the y axis. So it can rotate about the y axis, so you get 0, 1, 0, 0, 0, 0. Now the rotation passes through the y axis, so the moments will be 0, it is passing through the origin. So these other components will all be 0. Now you can also translate along the y axis. So q will be 1, right, and everything else will be 0. So this is a screw at infinity. Take the next one. So this is free to rotate about this axis, which is along the z direction. So this is 0, 0, 1, but a line which is in this direction will have a component 1 times a moment about the x axis. Okay, so you get a here. Should this be a? Should this be minus a? I have written this as 1, right? So this is along the z direction, not in the direction of the arrow. This is deliberately been done to mess you guys up. Please note, I note 1 here, that means this is along the z direction. If it's along the z direction, then the moment about the x axis will be in the positive direction. That's why this becomes a. So the sign is important. Finally, you have this translation along the z direction, so it is all zeros and 1. So these are the 4 screws which essentially represent the allowable motion in series. You could have combined this and this into a single cylindrical screw also. Okay, it's just a little bit more complicated because there are 2 variables in there. So with time you learn to do that. So now I am looking for the wrench LMN P star, Q star, R star that is reciprocal to all these 4 screws. So you take the first one, if LMN P star, Q star, R star has to be reciprocal to this screw, then I have no control on anything else except that I know that Q star into 1 must be equal to 0, right, because all the other terms are 0. So P star Q star into 1 must be equal to 0, so Q star must be 0. So that's what I am saying, Q star is 0, right. Now let's take the second one. So L, M and N, so M into 1 must be 0, right, and if you work with this you will get N into 1 must be 0. Now this is a little bit more complicated because what it essentially says is that R times 1 plus A times L must be equal to 0. Okay. So the wrench essentially that you are looking for is basically of this type, L00 P star Q and then minus AL. Now this has to be minus AL because this is L from this relationship. Okay. Oh, this I should write as Q1 star, but anyway. Okay. Now can you identify this physically? So definitely it's a wrench which is directed along the x axis. Okay. So it's a range directly along the x-axis, and what else? So it says that you can apply any amounts of twist about the x-axis. So if you essentially hold this, thing has gone off again. So if you hold this end of it and you push it along the x and y directions, it will move, but if you pull it along the x direction, it will stay. Okay. Another thing is that it says that if you wrench it any amount, if you twist it any amount about the x and y axis, it will not move too much. However, there is this combination of this corresponding to this AL1 term. It can only resist an amount of torque about the z axis which is in proportion to the amount of force which you apply about the x axis. Okay. So it's a little difficult, but you understand that finally the algebra operation or the arithmetic that you do with it is fairly simple, even to work on to evaluate such complicated structures like this. So that is the beauty of this tool, is that there's a large learning curve, but after the learning curve is there, it's over, then some of these things become very easy and can be reduced to simple linear algebra forms. The advantage of that is that it is very easily programmable once you have it. Okay. So I want to stop here now because the next two topics are working on serial systems and working on transformations, which I want to take up after the minors. Okay, on the 8th. All right, so we'll stop here today.